So today I will talk about generalized Ricci flow and what about generalized Laplacian. And as I promised, it's going to be some kind of elementary differential geometry with some physics words or some physics motivation. So what do we want to achieve? So I'll start with the first part, with this generalized Ricci flow. So we want the following thing. So imagine that we have a Courant algebroid. So if this guy is a Courant algebroid, and if inside we have a generalized metric, so each time we see such a situation, we want to have some kind of flow of V plus, of this vector subbundle V plus inside of E. So from that, we want to cook up some movement of this V plus as it is inside of E. So I'll write it slightly schematically that V plus now depends on T, which physics-wise is the logarithm of the scale of V plus. So what should this thing be? It should be, okay, imagine this is an infinitesimal deformation of V plus. So how should we see it? It should be a map, linear map going from V plus to the orthogonal complement. And I'll give it a name to this linear map, Ricci, depending on V plus. So that's how we somehow want to move it. And we want it to satisfy somehow two reasonably natural, obvious things. So such that the first thing is that if E is an exact Courant algebroid, so then this V plus is just a metric, Riemann metric and a free form, then we want this flow to be the usual Ricci flow or the usual one-loop renormalization group flow. So if E is exact, we want it to be the Ricci, or more precisely, one loop RG flow.
So this Ricci flow is defined with H?
Yeah, so that's why last time I didn't tell you what's happening when there is H, so this time I'll tell you precisely what happens there. So what I mean by that, let's say that if locally we have that our H is whatever, locally dB. I don't need to write it that way, but it's kind of nicer if I look at it this way. Then this slightly modified Ricci flow is that now both G and B move, or that when B moves, then H moves. And it is given by minus the Ricci tensor for this metric, but with non-zero torsion, with torsion which is H, or which is the dB. That's the torsion. So we take not the Levi-Civita connection, but metric connection with this particle torsion. Okay, so that's the first thing that we would like to satisfy. And the second thing, we'd like to somehow link this case of exact Courant algebroids to non-exact Courant algebroids, and there will be only one requirement, which I say that it should be compatible with pullbacks. I will explain what it means, but in particular, as a particular case, it should be compatible with isomorphism, so it should be a natural thing, so it should be somehow So what does this mean? Compatible with pullbacks. Let me do it this way. So imagine that we have some Courant algebroid over some M. And now we pull it back as a vector bundle somewhere. So suppose that we have some M prime and some map F that goes like this. And we just pull back this vector bundle. We get F star E that I'll denote by E prime. And now I want to make this E prime to a Courant algebroid again. And it's not in a way that it will be somehow compatible with the Courant structure, which is here. And now okay, one needs to think what it should mean. So first of all, say if you take two sections from here and put them back there and compute the Courant bracket there, it should be the same as first computing the Courant bracket and then putting it back. Then there is pairing. Well, pairing is we simply take the pairing which is here and pull it back to pairing which is there. So far so good. But there is one more piece of data in Courant algebra, that's the anchor map. And this is the only piece of data which is now not fully fixed by this pullback. Because what should it mean? You see, we can take a section from here and apply the anchor map. We get a vector field on M. Or we can pull back this section here, apply the anchor map, and we get a vector field here. So there are vector fields on two different manifolds. And so what is the requirement? I'm not going to write it down. I'm just pretending that everything is OK. So the only reasonable requirement that is now that if you push this vector field from here forward to there, we get the vector field that we get here by the anchor map. Yeah, that is actually what, yeah, this, what was the right word is those two vector fields should be F-related, I think. Yeah. Or should I write it down? Yeah, maybe if, just this one little thing, so if A is a section of E, then if you take the pullback of A and now apply the anchor map, which I'll write with prime here. So this is a thing which is not fully determined. This row prime needs to be chosen. But the only thing that it should satisfy now, that if we take F lower star, so we should push it forward there, that this should exist, and it should be, okay, maybe this is not the right, perfectly good writing, but that it should be equal to rho apply to A. So this rho prime is not uniquely determined. So this is what I mean by a pullback of a Courant algebroid. So it is not just whether to pull it back. There is a bit of choice. Actually, maybe that's not the standard way how to call it. So other people call it action of a Courant algebroid. They would say that this Courant algebroid here acts on M prime via this rho prime. So there is a little bit of choice somewhere. Okay. Anyway, have we seen such a thing? Yesterday, since I paid attention to my talk, I remember we did see. So example. What happens when for M we take a point? We saw an example where M was a point. So we take this thing, and over that, a Courant algebroid is a Lie algebra with this whatever pairing thingy. And now, for this M prime, we take G mod H. where H was a Lagrangian Lisa algebra in G. And now pulling back with the vector space like that, it will give us simply a trivial vector bundle, G mod H times G. And you see, if you recall now, like the Courant bracket for constant sections, for sections that are pulled back, is just the Lie bracket here, and things like that. But the anchor map is the only slightly surprising thing, slightly non-obvious thing, that it's the action of this Lie algebra on that guy. So that one we had to choose, and it was not totally obvious that that's what we should do. Okay, and what is that compatible with pullbacks? What? Yeah.
There's a question.
So this is not the pullback as like for Lie algebroids.
No, maybe I shouldn't. As I said, maybe pullback is not the right terminology, but let me still use it. It's only pullback of vector bundles, and then for the structure, for the Courant structure, there is some non-uniqueness. So that's a thing that one needs to choose. Okay, so what is that compatibility? So imagine that we have now here V plus sitting here, and it will give us we pull it back here. It will give us V plus sitting there. It will be what? It will be V plus prime, which is just the pullback of V plus. And now what do we want? We want that if we let this V plus flow in E, using this generalized Ricci flow that you want to define, and we also let this V plus prime flow in there, that all the time during that flow, it stays compatible. So this flowing V plus is going to be simply the pullback of that V plus here. That's all.
And that should work for any choice of rho prime?
Yes. Okay. Do we really need it? Let's say that we'll find a solution to this problem. So, yeah. It should, but as you said, it should work for any choice of rho prime, but which is anchor map for some Courant algebroid structure. So there is a cool.
Does it fix this equation which you search uniquely, these two conditions now?
A cheap answer is no. Now, a slightly better formulated question, but it will see in a moment what is the slightly better formulated question, would be that, yeah, then I don't know, but let's see. Also, as I put it this way, it is some abstract nonsense, right? That we know what it should be for the case of exact Courant algebras, and then we're just looking for something that would be compatible with this, and we hope that maybe it's reasonably unique. But if there is some physics behind, then hopefully it should be completely fixed by some physics picture. And I told you, I didn't disclose what it was, but I told you that if you have an arbitrary Courant algebroid and a generalized metric, it still gives some kind of two-dimensional model, some two-dimensional boundary field theory. So one should still be able to compute the renormalization group flow for that, and it should be somehow reasonably uniquely determined from Feynman diagrams, basically. So then, whatever we're looking for, if it makes sense on some slightly deeper level, then it should come also from this calculation, and it will. But it will happen on Thursday. So today, I'll just kind of show you a solution for the problem as it's stated. It's a nice thing. The problem looks reasonably easy. Well, the only trouble is that there is no solution. So unfortunately, so what is the problem really? There is a one little thing which was noticed by many people. I'll give you like references a little bit later. The trouble is that we cannot really find a fully natural, this generalized Ricci thingy that would depend only on the Courant algebroid on the generalized metric. One needs to pick some choices. This looks ugly, but I'll explain how to get rid of that ugliness. So there is this and plus some, let's call it data.
But picking additional choices doesn't mean there's no solution. You mean there's no canonical solution then?
Yeah, there is no canonical thing. So what do we need? I'll tell you what kind of data it might be. One possibility is to choose some connection on this vector bundle E. That's a perfectly good choice. There is some kind of best choice that I will tell you in a moment. But let's pick some data. Then, so what is happening here? In this situation, we have this, we will not see this. We would have here this generalized Ricci V plus and data. And so what kind of compatibility do I want here? I would take this generalized Ricci with pullback, so with F star V plus. And I also want to pull back the data. Like if it's a connection, then we know how to pull back connection easily. So also F star of data. And we want whatever this to be equal to that after we pull it back. So F star. So this should be slightly more complicated equation. But now, how to get rid of the data? It looks fishy. So let me add something to this equation. So what one can possibly have there is some kind of trivial term, so term that doesn't do anything. So if you just apply infinitesimal diffeomorphism, meaning a lead derivative with respect to some vector field, it will not really change anything. And physics-wise, it depends on somewhat of a regularization scheme or whatever people call it. So this is really nothing. We can always have this kind of thing. So lead derivative with respect to something of G plus B. And that B itself is not very terribly well determined. So we can also add there plus D of an arbitrary one form. And this X and alpha is kind of like this additional data, which is slightly random, which is somewhere behind. So what is now the real requirement? So there is part 3, a third requirement. Once we have it with this additional data, we want that the flow, say, is independent of the additional data modulo a term of the sort, so modulo an inner derivation of E, meaning modulo a thing that looks like that we take a section, whatever section of E, and we apply this infinitesimal automorphism. That's exactly like for this whatever standard Courant algebroid. If I take pair X alpha or X plus alpha, so it's a section of, so here X plus alpha is a section of T plus T star. And the thing, this red thing that's written there is exactly how moving V plus infinitesimally with this derivation, how it changes G and B. So this is what we want. Okay, now, finally, the problem is formulated. So it's a little bit, because of this additional data, it's slightly convoluted. And that's the reason why it took some time, probably, to sort it out.
And as you say, so with x and alpha equal to 0, there's no solution. So that's true then.
Yeah, so this might be slightly confusing. So in the case of let's say in the case of exact quantum algebroids, there is a preferred choice of this additional data. So to say that we simply discarded that part, that we don't have it there. But if you want it to work for arbitrary Courant algebroids, then unfortunately there is no preferred choice. So that's roughly the answer. Okay, so that's the problem. And if you find a solution, it will automatically say that Poissonly T-duality is compatible with randomization group flow, because Poissonly T-duality is exactly the thing about pulling back, things like that. So I showed you what Poissonly T-duality was in this case. And so if you have V plus inside this, and then we have this V plus inside here. So here it will flow, there it will flow in the same way precisely. But here it is this Ricci flow, the RG flow, so the thing is somehow independent of H. Okay, that's somehow the physics motivation, but math-wise, this is what we want. Now, what is this? What is the data? As I said, we can simply use a connection, but say the minimal choice that was observed by Mario Garcia Fernandez, that we should use what is called a divergence operator. So what is that thing? It's denoted by div, which might be slightly confusing, and it's a map going from, which takes a section and computes its divergence, sort of. So it computes a function and such that the divergence of f, sorry, a function times a section is f times div a plus now rho a. So this is a vector field which can now act on f. For an example, div a, we can take, if you take an arbitrary volume form, let's call it mu, and then take its Lie derivative with respect to whatever the corresponding vector field, and then take mu inverse. That's a divergence. So it's easy to see kind of immediately that it satisfies these kind of things. Okay. No, sorry, yeah, I should repeat it. Yeah, so it's a bit, as you said, the problem is that this definition looks slightly strange because it only talks about the anchor map and doesn't say anything about the bracket. Whereas normally a divergence for vector fields, yeah, it's a cocycle, whatever one can say for the bracket. So is it like the right thing? The answer is that yes, this is enough. Even though this one will satisfy slightly more, it will also be compatible somehow with the bracket. But in general, it's enough to have such a thing. But yeah, maybe we shouldn't dwell too much on. As I said, this is probably the best choice of the data, of this additional data. But there are easier or more straightforward things like a connection, but which just contains more information than this. This is some kind of maybe. If one starts with a connection and then we take its trace, sort of, then we can get a divergence. So it's a smaller thing. Now, yes, so what is the solution? So let me write down the solution of the problem. So first I will write it for the case, still to like delay slightly this final revelation. I will write it for the case when the Courant algebroid is just a Lie algebra, so when M is a point. So if M is a point, this guy is a Lie algebra, so which is the split by this generalized metric to direct sum of two vector subspaces. Then this generalized Ricci thingy of V plus. So what is it? Okay, there is minus sign. And then I'll draw some diagram. Now, how should we read this diagram? So those trivalent vertices, they are structure constants of G. G is something with an, let's say, Lie algebra with an inner product, with a pairing. And those pluses and minuses, they are orthogonal projections to V plus or V minus. And so how should one see this? So this guy is a map going from V plus to V minus. We start with an element from V plus, so it is, it just doesn't observe this orthogonal projection to plus, but I still write it there, so it just goes here. Now it somehow becomes an element from wedge 2 of G. Then we apply this plus projection here and minus projection there. Then we compute the bracket. And then we take just the minus component. That's it. Or another way how to see it, or how to read it, if you see it as a bilinear form, so if you feed inside an element from V plus and an element from V minus, then this is going to be, there is this circle here, so it's going to be trace of whatever add of that and add of this, but together with these orthogonal projections. And maybe no. It's an exercise to write it. No, I don't know. I think it's a perfectly normal thing to read this kind of diagram in that way. Also, like it's say suggestively, it's a one-loop diagram. And yes, it is a one-loop diagram in Chern-Simon's theory with some suitable boundary conditions, but let me leave that for Thursday. So that's it. And now, if M is not a point, so general E over M, then all that happens is that this, if I write this first schematically, so it will be the same kind of thing. And plus some divergences, some terms that contain divergence. And frankly, I find it totally useless to write it down completely as expression. So that's why I'm going to do it. But just don't expect anything. So more precisely, what the thing is. Okay, this first term is, okay, there is minus, and as I said, that cycle one can understand this as a trace. The trace is, okay, let me write it as a trace over V plus, and, sorry?
So you are writing
Yeah, as I said, that I find it completely useless to write it down, and that's why I'm writing it. Or maybe, yeah, so I should write it like this. So Ricci V plus, when we fit inside a section of V plus and a section of V minus. So this plus and minus just stand for, it's just a visual hint. So there is this trace over V plus as we somehow come, if you just try to read this thingy. So where do I have it? So we take our element from V plus, we act on it with that, or we take the Courant bracket with B minus, then I will not write it down. This means that we take the orthogonal projection of the result just to V minus. And then we take the bracket of the result with A plus, and we want to stay in V plus, so we then take the orthogonal projection to V plus. So this kind of reading of this term, and plus there is a divergence part which looks like plus divergence of B minus A plus, where we take only the plus component and whatever minus rho B minus. So it's a vector field which acts on a function, which is divergence of A plus. Okay, I wrote it down basically just to show you that it was not a good idea to write it down. Also, one needs to think a little bit about why this is actually well-defined, because here we have this Courant bracket thingy, but we want to take trace. It's like over vector space, or at each fiber we're taking trace. So this thing should be really C-infinity linear. So it should be like a really pointwise operator. But that's not difficult to show that it satisfies all the needed properties. So it's well-defined. And it solves the problem. Okay. So the outcome of this just for me is that Poisson T-duality is compatible with the randomization group flow. And one can also see some of the general strategy for showing that Poisson T-duality is compatible with whatever. That take your whatever, which is defined for ordinary two-dimensional sigma models, phrase it in terms of that exact Courant algebroid. It's not going to be big work because it's just G and H is the same as an exact Courant algebroid plus a generalized metric. And so if you have some other things, then just somehow press it inside. And then try to formulate it in a way that would work for arbitrary Courant algebroids, not just for exact ones, but for arbitrary. Yes, there's a question. I will repeat it. So.
Do you have any ideas on how to do stuff with logic?
Okay, so the question is whether this was a one loop. That's a one loop R thing, and how to do it for high loops. It's a very good question. I don't know. I still imagine that it should work. And also, if I said that okay, this was some random solution of a random problem, but if I say that at the same time this is actually RG flow of some well-defined two-dimensional model given purely by the Courant algebroid and its generalized metric, then one should be also able to compute that RG flow to any number of loops. And I'm not aware of that being done, but maybe it actually is done. I don't know. But it's a good problem. I don't know. Okay. And there's one more thing that I promised for today. That was generalized Laplacian. Yeah.
There's one more question.
Thank you. Just to be sure, you said in this solution, the extra data is taken to be this divergence operator.
Yeah, exactly.
But you might write something else.
Yeah, for this solution, it's kind of minimal in the sense that divergence is the minimal possible data that one can use. And yeah, so I should, as you said, I should write here div, and I was not very clear about this thing. So here the divergence that is used here is simply 0. So that's a convenience of a Lie algebra that 0 is a preferred divergence. But for other Courant algebroids, usually there is no preferred divergence. So that's why there is some kind of problem.
And is the most general solution also parameterized by some divergence, or could there be some other solution to this given problem here?
Probably, you see, okay, what you can do, there, as I said, is it still somewhere there? This modulo an inner derivation of E. So if one say, produces like a section of E by some super convoluted way, and then simply add this thing to the Ricci flow, to this generalized Ricci flow, it will still be a solution. So if you make like some very complicated x and alpha computed by some horrors, then this will still be a solution. But now, say if the question is that this is not so well-defined question, but still whether modulo these things, whether that's the unique solution, then I don't know. And maybe it's not. Also, I don't find like a very pressing issue in the end, because what I can say that this random solution actually does have some kind of physics meaning coming from some Feynman diagrams in the end, but not today. So this generalized Laplacian. So there are some keywords that I can write there. So one of them is dilaton. And the other keyword is gradient flow. But in some sense, what we want to solve, and sorry, can I step back? I wanted to now say, like, at least I should cite some people, I guess. This is like quite bad not to mention anybody. So we were working on this problem with Friedrich Wallach, who is here. I will write his name in a moment. But then, because of my ignorance, we didn't notice that this kind of thing appeared long before that in the work of other people. So just the thing. So what are some names that I should write? So there is some kind of founding paper by Coimbra, Strickland. Sorry, that's COI. Yes, sorry. Strickland, Constable, and Ordram. There are other foundational papers by Jurcho and Vysoky. There is this already mentioned Mario Garcia Fernandez. Then no. So we were not the first ones, but we were the last ones. So that's all. So it was me and Friedrich. And in fact, this expression, and in the right context, it's not just randomly this expression, but somehow in the right context, and that's some of the most important part of the story in some sense. that appeared, that is their names, Svetsos, Siampos, and Thompson. So there are many people who worked on similar stuff. So I don't know what I can say, like what we did first. Maybe we were the first one who formulated it for arbitrary Courant algebroids. I'm not, possibly hard to say. And maybe this formulation of the problem, like this being well defined, that what we're looking for somehow, that is stupid additional data, how to get rid of it, what we actually want from the solution. We want it to be well defined up to inner derivations. But those other people, they came up with their own properties, their own reasons for introducing such things. Okay, and let me now get back to this generalized Laplacian. By the way, when should I end? Is it now or when should I end?
In 17 minutes, maybe?
Oh, so I should really like talk for an hour or something?
No, if you like, certainly, but in principle, it's fine.
But you know, as how it goes with speakers, I can talk forever, but
Maybe for 17 minutes?
okay. So, how about this generalized Laplacian? So I wrote some words here, but one thing that is somehow ugly over there is that there is this additional data. Nobody wants some strange, unnatural solution. So, natural problem here is, so what is actually natural here? What depends only on this Courant algebroid and the generalized metric? So, say a fully that would in the end explain this generalized Ricci tensor and also hopefully this additional data and things like that. So one fully natural object that exists here is it's a second order and formally self-adjoint differential operator, something very easy. So which acts on half densities on M. So if it wants to be formally self-adjoint, it needs to act on something where there is a natural pairing, and half densities is the simplest thing where there are natural pairings. So it goes from half densities on M to themselves, which is defined just in terms of V plus and E, as it is in E. Unfortunately, we never found a invariant formula for that. Like the object is invariant, but formula that we found uses trivialization, some trivialization or some frame of this vector bundle. But okay, never mind. So we choose the orthonormal frame. There is some whatever. So this is off V plus, and it will not be really used, but also some, maybe put me here some bar or something of V minus. And this operator, it's again a useless formula to write down, but the formula is again, it's sort of suggestive, so let's see. So there is a part that contains derivatives. For some reason there is 4, but it's not very important. So we somehow write what would be a Laplacian if we just use these pluses, so just this orthonormal frame of V plus. Yeah, it is second order. It is formally self-adjoint, but it very much depends on the choice of the frame. It's not natural. But then there are, if it wants to stay formally self-adjoint, we can, and if it wants to have just the same symbol of this guy, we can only add a function to that. So plus some function, and what the function is, the function looks kind of nice. There is like a symmetry factor 1/6. And there is this diagram. And there is again a symmetry factor 1/2, and a similar diagram, but with 1 minus. So what are now these vertices? Those vertices are like things of this form. Okay, A, B, C. So if you take 3 constant sections of our Courant algebra, now we have chosen those chosen frames, so that's why we can talk about constant sections. So these kind of things are fully skew symmetric. That's what we're putting to these vertices. Contract them, we obtain this. It looks random. It looks like a two-loop thing, as it's.
So how does the first, for example, or any of these two look like in detail?
So let's take this first one. So I would, whatever, let's call it F. Let's say A, B, C. It's a function on the base with 3 indices. This thing, I'm going to just define something. So this would be like this: E, A, E, B, oops, sorry. E, C, the thing, right? And now, what I mean by that this thing is we take F, A, B, C, F, A, B, C, and because of whatever, there is a different order or something here, there is minus. Yeah, times 1/6, minus 1/6. Sorry? Yeah, repeated in this are summed over. Yes. And the second guy looks kind of similar, but there is one minus thing inside. And does it make sense? Maybe. Yeah, so this thing looks suggestively as a two-loop thing. In the case of a Lie algebra, when the Courant algebra is a Lie algebra, then this ugly term is not there. It's just this thing. And yeah, I'm not quite sure what is the physics meaning of this guy. Let's see about it on Thursday. You'll tell me. And okay, so what are some basic properties? Say if E is exact, so meaning that this V plus corresponds to some G and H, then it's a thing which is quite recognizable in string theory, which looks like 2 times the ordinary Laplacian given by the metric. Let me put there this G, and then there is some function. So there is minus 1/2 times the scalar curvature of the same G, and plus 1/4 and times, let me write it like H squared. It's like 2 H's, and indices are contracted with the metric. So in particular,
does this H square correspond to one of these terms in the end?
I don't quite remember, sort of, kind of, but maybe, I don't know. It definitely looks like that. There are 3 indices and there is a contraction. It's not like that completely easy, but yeah, I think that, okay. Let me not talk about it. So why is it interesting and how it relates to the other stuff? So first of all, if sigma is a half density, we can define this axial functional, so V plus n sigma, a thing that one can write down using a kind of second order differential operator. So I guess minus 1/2 is the right thing to write the integral over the base. And sigma times this Laplacian applied on sigma. So in the case of an exact Courant algebroid, again, so in this case, so if we set that sigma is exponential minus phi, phi is what stands for dilaton, and times the metric half density, the thing that comes from the metric. So then this guy is the whatever, is this low energy string effective action. Yeah, I said that we take those two h's and then contract the indices using the metric, using G. Okay, so to finish all this story, the talk should finish soon. So let me just say how it relates to this generalized Ricci flow and how it relates to some more stringy stuff, as one should expect from such a thing. So first of all, so the first thing, so if we fix a nowhere zero half density sigma, this will give us a Riemannian metric on the space of all generalized metrics, on the space of all V pluses in E. How is it going to look? So just imagine that we take a variation, a small change in V plus, so a map which goes from V plus to V minus. So something like this. And let's take it twice. And we want to somehow compute this inner product of this way, say, with itself. So what we can do, we can simply pair those things, but that way we'll get a function on the base. You know, it's like a map going from V, or it's an element of V plus tensor V minus. A section of that thing, we take it twice, so we can contract V pluses and V minuses together. So I can write down something like delta V plus. V plus. Sorry?
What are you talking about?
I want to define this. I want to define a Riemannian metric on the space of all. And why I'm doing it, because I want to show you that this generalized Ricci flow is a gradient flow, and it's the gradient flow of this would-be action functional that I wrote there. So that's it. So let's just, this is the only natural thing that one can write down. It's negative definite, so that's why I need to put here minus, but whatever. This is a Riemannian metric now on this infinite dimensional space of all possible V pluses in E. And then what we get is that the gradient of S V plus sigma. So this sigma is fixed, but V plus is not fixed. So it's a function on this space of all possible V pluses. So if you compute its gradient, but we just take the variation of this guy when we vary V plus. So this guy is the generalized Ricci flow where the divergence, which is given by sigma, so it's given by volume for my density, so it's given by sigma squared. So that's one thing. So the gradient of this guy is the generalized Ricci thing. That's already one nice thing. Now the Euler-Lagrange equations of S V sigma that's roughly what's already written here. So they are that this generalized Ricci tensor with the divergence which is given by our sigma. So this is 0, and there's the second equation, that's the equation for sigma, so which didn't show up here because here sigma was fixed. And so this thing is the whatever string background equations if E is exact. So it's some conformality equation, conformality condition for our sigma model. From that, if one looks at it a little bit more closely, one can see that Poisson-Lie T-duality is compatible with those string background equations under some unimodularity condition. A unimodularity condition. So, which in the simple case where I was talking just about Manin pair, it should be that H is unimodular. It shows up only because there are those half densities and we need to somehow cook up. We need to somehow pull back half densities from somewhere to somewhere, and to make it work, we need to have invariant half density somewhere, and that's this unimodularity. Okay, so this was like a quick thing, but that's roughly how it applies. And that's all for today.
Thank you. I propose that we ask first the online participants to ask questions. So just unmute yourself and ask. So if this is not the case, then there's at least one from here.
So out of curiosity, is there a problem here? Is there a problem that the generalized Ricci flow plays the role of that the Ricci flow plays in Perelman's and Hamilton's work on the Poincaré conjecture?
You think like whether all this stuff can be somehow now used for some like high-scale math?
Geometric topology or something, yeah, or some.
I would love if it happened, but I don't know.
Okay.
But yeah, so maybe something is that hopefully this Ricci flow is, one can say, is compatible with some like a Dirac relations or Courant relations. Roughly speaking, it should come from here, and maybe it should somehow show up somewhere. Yeah, okay, I didn't answer your question. That's very good.
My question is, okay, you show us what is generalized Laplacian for the exact Courant algebroid in the relation to the string backgrounds. What for general Courant algebroid? Is there a relation to strings?
So one thing, if one takes a transitive Courant algebroid, which means that the anchor map is surjective, so it's then okay, and one also needs to now take a generalized metric which is of some particular rank. So this is these things like show up in in heterotic string probably also. So then one can understand it as now it corresponds to like this G and H as before, but there is also some connection somewhere. So then if one plugs it in that case, you'll get also the right term, like this F times F term. But otherwise I don't know. Let's say the hope is always that when we take the how to put it, that one should somehow take it seriously, that there is actually some kind of well-defined two-dimensional physics model determined purely by the Courant algebroid and generalized metric, and maybe by some additional stuff if you want to have additional stuff, if you have maybe some supersymmetry or something like that. And that this thing should show up in the conformality condition for this two-dimensional sigma model. We'll see something like that on Thursday, but then I hope that somebody will really solve it.